Welcome everyone to the first of two videos on nuclear chemistry. In this video we're going to be talking about nuclear decay and just some of the notation and things like that we're going to deal with when we talk about nuclear chemistry. Okay, so our notation typically that's used for describing atoms when specifically talking about nuclear chemistry is something like this. Either the symbol, so for lithium, for example, the symbol is Li. The subscript here on the left and right, so we put subscripts and superscripts on the left, right? So the subscript here on the left is the number of protons, right? Which is also equal to the number of electrons, right? Because my atom's neutral, I have to have the same number of protons and electrons, right? And that's your atomic number, right? Your number of protons, your atomic number, right? And then the 7 here is your atomic mass number, right? This is the number of protons plus neutrons, right? So for lithium 37, right, all lithium, all versions of lithium, if you will, all isotopes, I should say, right, different isotopes of an atom, right, is what we'll be talking about, right? So an isotope of lithium is lithium 7, right? So how I'd say this is I would call this lithium 7, right? Because it being lithium implies there's 3 protons, right? The number of protons is unique to a given element, right? Each element has its own unique number of protons, okay? So if you change the number of protons, you're changing the element, right? So the element name and the number of protons are linked together, right? That they are giving the same information, right? So lithium 7 is telling me, right, I have 3 protons, and 7, the atomic mass number here, right, is telling us the number of protons plus neutrons. So if there are 3 protons, that means I have to have 4 neutrons, right? And so on the picture here is sort of the picture of the nucleus, right? So I got, my 3 protons with the plus signs, right? And then I have my 4 neutrons, right, that are neutral in there. So I have a total of 7 particles, if you will, in my nucleus, okay? And that makes up lithium 7. Okay. So, I'm talking about types of radioactive decay, right? As you've kind of been introduced through life and different things, right? Nuclear decay, radioactive decay can be very harmful, right? It's because when nuclei decay, right, when they go from a higher atomic number to a lower atomic number, they emit radiation. There's a variety of different types of radiation. Some are more harmful than others. Okay. So the main types of radiation we'll talk about in this class are things like alpha particle radiation, that is a helium nucleus. Okay, so an alpha particle, given by the symbol alpha here, is just a helium nucleus. Okay, so that is a type of radiation. Okay, when things decay, they can emit a helium nucleus, right? There's beta particle decay, that's given by that symbol beta. And that's the emission of an electron. Okay, so an electron is a beta particle. Okay, called the same thing here. Then there's neutron decay, where you emit a neutron, right? Positron decay, where you emit a positron. Okay, positron is a positive electron. Okay, and then gamma decay, right? And gamma decay is just high energy photon, high energy radiation, high energy light, right? There's like ultraviolet light or even higher energy kind of light, right? And so those are the different types of decay that one can have. Okay, so an example of alpha decay, right, is given in this nuclear reaction here. Again, notice the subscripts, right, are these atomic numbers, right, for the different nuclei, and then the superscripts are the atomic mass numbers, right, for these different nuclei. Okay, and see here that this thing decays into some smaller nucleus plus then a helium particle. Okay, Beta decay, what you have here, right, is you notice that my my atomic mass number here does not change at stage 14, but I now go from having 6 protons to 7 protons, right? And essentially what's happening here, right, is you have you can think of this, if you will, as a neutron decaying into an electron and a proton, and that electron getting kicked off, right? Not exactly what's happening here, but like you can think of it that way, right? That this neutron decays into a proton and electron, and so you lose 1 neutron, you gain 1 proton, right? Which is what changes you from a carbon to a nitrogen atom, and then you kick off that electron. Okay. Gamma decay, right? So gamma radiation, this often, any type of nuclear decay includes gamma radiation, includes these higher energy photons, okay? But if you have some nuclear reaction, if you will, that just emits gamma particles, then there's no change to the atom, okay? Because this light isn't changing the number of protons or neutrons or electrons on your atom, right? And so gamma decay is just emission of light. And again, often, right, the alpha and beta decays that we just showed, those type of decays often are going to be emitting gamma radiation as well. Okay. So, summarize these 3 most common types of decay, right? Right, the charge of the decaying particle, an alpha particle, is a helium nucleus, so it's got a +2 charge, so it's got 2 protons, right? The beta particle emission is a -1 charge because that's an electron, right? And gamma particle has no charge, right? Mass of these guys, right, are based off the mass of the nucleus of a helium, mass of an electron, right? Light has no mass, okay? Focus on kind of this relative penetrating power here, right? So the smaller the number, the less penetrating power that this particle has. So an alpha particle has a penetrating power defined as 1. Gamma particles have a penetrating power defined as 10,000, okay? Right, so there's a big difference in the penetrating power of these things, okay? An example of what could stop some of these things, right? So alpha particles can be stopped by like a piece of paper, okay? Beta particles need something like a thicker piece of like wood or something like that, right? To potentially stop beta particles. And gamma radiation need like a thick slab of concrete or lead or something of that nature to try to stop gamma particles from penetrating, say, into your body, okay? Right, now the convenient thing with all of these is the fact that the more penetrating something is, the less harmful it happens to be, okay? So gamma particles, right, while harmful, gamma radiation can be harmful to your body, and too much exposure to gamma radiation for too long a period of time can cause harmful effects to your body and potentially be lethal, okay? It takes a lot of exposure to the gamma radiation and over longer periods of time for that to occur, okay? While, say, alpha particles, if somehow they get into your body, are very, very harmful, okay? Because these things are very reactive and will cause lots of damage to your body, okay? But the convenient thing is you know, you can stop it by wearing clothes, right? Regular clothes or things like that would easily stop alpha particles from penetrating into your body, right? And so you don't have to worry so much about those things, right? And so, yeah, so it is, you know, sort of convenient, the fact that the more penetrating something, the higher the penetrating power something has, right, the less harmful it is. Yeah. But that, again, that's not to say gamma radiation isn't harmful. It is, right? So you don't want to stand next to nuclear waste for a long period of time or something like that, right? Because that gamma radiation can definitely be harmful to you. Okay.